All right, guys. So here, I remember you guys had a questions regarding just how what makes amino acids polar, non-polar, aromatic, and aromatic, and these things, and also questions about primary, secondary, tertiary, and quaternary structure. So I'm going to go with more details and take my time to explain this. All right. So let's just go here into just what an amino acid looks like. Well, amino acids are a compound that has a carboxylic acid, so actually a central carbon atom, and then has a carboxylic acid, the carboxyl group here, an amino group, single hydrogen, and the variable R group. And this R group are different types of functional groups, and these are variable. And in humans, there are 20 of them. So we basically have 20 different amino acids, and the only thing that differs between amino acids is the R. So let's take an example. So if we have here alanine, the R here is CH3. The R, for example, in leucine is the following. The R here of tyrosine is CH2 with this benzene ring and an OH. But you can see that the main backbone, so the central carbon is there, the amino is there, the carboxylic acid is there, and the hydrogen is there. That is always in all amino acids. That doesn't change. So the R group really dictates the differences between amino acids because that's the only thing that's changing, right? So let's imagine here, if you look at the R group, let's take a look at these R groups. These guys all here have carbon and hydrogens. Carbon, hydrogen, and also carbon hydrogens. And here you don't have a hydrogen. So you start looking at these R groups that these are all carbons and hydrogens. One thing we know about carbon and hydrogen is that when they create a covalent bond, carbon and hydrogen have a very, very similar electronegativity, meaning that they have the same affinity towards an electron. So when they bound together, they will share this electron quite nicely with each other, meaning that there's not going to be, any partial negative or positive charges. So they're going to become very non-polar. Well, because their R group of these guys, these amino acids are non-polar, they become non-polar. But if we have a look at here, these guys, which actually have now an oxygen there, an oxygen there, and the oxygen there, oxygen is very selfish. It loves to bring oxygens more to itself, so it's creating these partial negative and positive charges. So they're becoming polar. So that's why these are polar, because you have polar groups here, which is the oxygen. Now the charge, quite simple, meaning that the R group, you have actually a negative charge over here. So you have a negative charge there, you have a negative charge there, and there. So they're quite easy. So now the difference between these guys over here in this row and this other row is being either aromatic or non-aromatic. Aromatic basically means that their group is basically has these rings. So we call these benzene rings. So as you can see, you have a benzene ring here, there, and basically here as well. You have a ring. So they enclose each other. So that's what it means aromatic, that they're actually enclosed. Non-aromatic, they're not closed. They're quite linear, as you can see here. So the same thing goes here. These benzene ring is all composed of carbon and hydrogens. Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. So very nonpolar. Same thing here, carbon and hydrogen, you have nitrogen. Nitrogen also has a very similar electronegativity to carbon and hydrogen. So it's mostly nonpolar. But you see here now, this is exactly phenylalanine and tyrosine are very similar to each other, but the difference is that you have an extra hydroxyl group, which has an oxygen. And this now then turns this whole polar because oxygen is very polar. That's why these guys become polar. Here, basically, now the ring has actually a very positive charge. So these guys have special functions. This methionine and cysteine is simply because they actually have these, how can I put it, sulfur. And sulfur, what sulfur does, it loves to create bonds with other sulfur molecules. So if, for example, methionine and cysteine are together, they're going to directly connect with each other through sulfur. And that's called a disulfide bridge. So di meaning for two, sulfide for sulfur, bridge. So they create a bridge with each other. So two sulfurs create a bridge. So disulfide bridges. That's why they're special. Proline has this very amazing R group over here, which flips around. That's why it's special and it's hard to recognize, but that's the only one that you kind of have to memorize a bit. That proline has a very weird structure in a way sense that this is very flexible. That's why it's quite special. So keep that in mind. So now let's talk about peptides, about protein structures. So you have primary, secondary, tertiary, and quaternary. So primary structure is literally just the sequence of amino acids. That's primary structure. It's basically what are the amino acids that are making the protein. Because we know proteins are macromolecules that are composed of repeating units of amino acids. So hence the primary structure is the sequence of it. Is it phenylalanine, tyrosine, histidine, lysine, etc. That's the primary structure. Secondary structure is that now the R groups and basically the other R groups within the amino acids, there some of them are polar and some of them will start creating these hydrogen bonds because they're you're polar and you're polar and we have basically you have a partial negative charge and I have a negative and a partial negative charges. Let's start forming hydrogen bonds. And this hydrogen bonds kind of pushes the protein to come closer with each other. And when they get closer to each other, they create these nice structures like the helix or a sheet. So basically, helix becomes like this really nice um, formation, and secondary structure is more than beta sheets like this. So secondary structure is literally governed by hydrogen forces, and hydrogen forces are the one that are pushing them to kind of fold fold with each other. Now, when things are folded, amino acids that were far away from each other can be now more closer because they're folded and it can be pushed more. So I'll give you an example. So for example, this amino acid and this amino acid were far from each other. But when they're folded, now their R groups can be close to each other. So for example, here, for example, imagine this is positive and this is negative. Oh, they're gonna create an ionic bond. Let's imagine this is a sulfur or this is a sulfur. They're gonna create a disulfide bridge. Or this is polar and this is polar, or this is non-polar, this is non-polar. They're gonna love each other, they're gonna squeeze together with each other. So tertiary structure comes after this is now folded, and certain amino acids that were far from each other are closer, and now other forces like more hydrogen bonds, or ionic bonds, or disulfide bonds, or uh, or basically ionic bonds, or all these things can now kind of push the protein more together. That's the tertiary structure. So difference between secondary and tertiary. Secondary is just governed by hydrogen bonds, and they basically make them fold into the helix or beta sheets. Once they're folded, now amino acids that were far from each other are more closer, and now other forces can come into play, like ionic forces, more hydrogen bonds, non-polar forces or polar forces, disulfide bridges. That's the difference. Quaternary structure is a structure that not all proteins have. Only proteins that are made from different subunits have quaternary structure. For example, this protein is made of four different units. So quaternary structure is basically how this protein folds with the other subunits. So some proteins like myoglobin, which is made of just one protein, actually no, only has doesn't have a quaternary structure. It only has a primary, secondary, and tertiary. All proteins have primary, secondary, and tertiary. However, quaternary structures, basically these guys are only found in proteins that have more than one protein together. So for example, hemoglobin is made of four proteins. So hence they have a quaternary structure because there are four units and how they interact with each other is the quaternary structure.